Okay, so what are the trabecular groups in femur? Can you name any? I think you might have forgot it. So I will just give you an introduction on that too. So let me start the PPT. Fine. So bone orthotropy. Uh, so trabecular orientation. So here we are going to look into the trabecular groups in the proximal femur. So here we can see principal tensile group, principal compressive groups, secondary tensile groups, secondary compressive groups. As the name says, those are the groups which come into play. These are the trabecular orientations in the femur. So here you can see a small region where there is absence of trabeculae. So do you think absence of trabeculae can result in weakening of that area? Like, can you say that that's a weak area? Hello, can you hear me?
Yes, we can hear.
Okay, so there you may find only very less trabeculae. What do you call trabeculae? Do you know what is trabeculae?
No, sir.
No, sir.
Okay, so I will take you to the last slide where I have actually explained it in a more scientific way. So trabeculae is a supportive and connective tissue element. Okay, so that's actually what forms cancellous bone. So it helps in the formation of the bone and the healing. So the basic thing is trabeculae. So the orientation actually governs the material properties to be specific. So here you can see there is a lack of trabeculae in that particular Watts triangle area. So that is more. Yes, yes.
Yeah, you just
Yes.
look at you have pictures of the slides. Just
Yes.
move a little bit. Yeah. So this is trabeculae. Okay. Take one portion. Say you just take one sort of little box.
If you go to the principal compressive group, that is the first group. So here you can see first group is principal compressive group. Here you can see the trabeculae microstructure. So here there is more presence of the matter. You can see matter, isn't it? So
no, it's bone mineral. It's the solid part.
Yeah, mineral. Yeah.
Oh, so
Yeah, solid
bone,
yeah.
Bone exists in two phases, the solid and the liquid. So if you take one small sample of bone, depending on the on the bone mineral content, what part is fluid and what part is solid. So it's a porous structure anyway, the cancellous bone. And say if you take one unit cube, that is one trabeculae. Okay, and the orientation of these trabecules are basically what we call as trabecular orientation.
Trabecular orientation.
Okay, so how these unit sort of can consider it as a cell, a unit volume of bone is oriented. That is trabecular orientation, and that is why it is also called, the other name for cancellous bone is trabecular bone.
Trabecular bone.
Trabeculae is a unit volume of
yes. It's like singular and plural. Yeah. Okay.
Carry on.
So here you can see here we have considered each trabeculae from each principal groups. So you can see the distribution of this particular mineral. So at the region near the Watts triangle, you can see there is almost no mineral over here. It's like as compared to other groups. So I think it's more clear over here that in the region near the Watts triangle, the trabeculae is almost not present over there. That's why we have got a area of absence of trabeculae. And other trabecular groups, the only trabecular groups are principal tensile, principal compressive, greater trochanter group, secondary tensile, and secondary compressive group. So does this trabecular orientation define the what you call define anything? Do you think so? Like does this orientation define the material property orientation? Does it govern it? Hello. I need quicker replies, otherwise it will take more than 30 minutes.
Yes, I think they
Yes,
should.
sir.
I mean, they should define the strength of the bone.
Yeah, isn't it? It's more like it orientation in the sense it gives.
Yeah, not only strength, the first the property, it will influence the material.
Material property.
First comes the material property. Okay. So the orientation will actually define the material properties. And orientation means it has certain direction, and obviously what we assume as an isotropic assumption, it's purely an assumption. Okay, for bone, cancellous bone. It will, and assuming continuum. Both things are not valid if you really look into the microstructure of the microscale model.
Yes.
Okay.
So this particular. Yes, sir.
The moment you go inside in the microscale level, it is a mixture of solid. It's a porous material, and obviously the orientation of the trabeculae will dictate differences in E1, E2, E3. Okay, the principal directional Young's modulus, elastic modulus, will be different. Okay, as well as other elastic constants. Right?
Yes.
And that, to what extent it affects, different analysis, that would be explained to some extent by Sebi.
Yes. So as we already mentioned that it's a porous material. This trabeculae is porous.
Yeah,
so
please move ahead, Sebi.
Yes.
Stuck
So,
in one.
Yes.
Yeah.
Yes. I mean, I won't be talking more about the other slides because I'll just present. I won't read the material. So for orthoporotic patients, this particular microstructure becomes more porous, and this trabecular orientation actually governs the material property prominently for orthoporotic. Orthoporotic means like for the people who have got lesser bone density. So osteoporotic. Sorry.
So you can from this figure you can understand. So if you say look at 1, 2, 3 compared with 5, 6, 7. So obviously 1, 2, 3 is more solidly built trabecular orientation. Okay.
Yes, sir.
So in 5, 6, 7, as more porosity sets in, it will substantially affect the directional properties. Okay, the more solid it becomes, the orthotropy and isotropy, they merge, come closer to each other. So for macroscopic models, the isotropic assumption is reasonably proved to be acceptable within 5% error. That I will give you as a supportive paper later on. But if you are handling, making a model of highly osteoporotic bone, then isotropic assumption is very less acceptable or very less valid. The orthotropic properties will become more and more important for different kinds of evaluation. Okay?
Yes. So as we all know, these are just basics. So I'll just skip this one. So I have just shown the the elastic tensor over here. So here, as I already mentioned, is bone isotropic in nature? I mean, in reality, it's not isotropic because in the microscopic level, bone trabeculae is porous. So we can't actually say it's isotropic. And there are several studies which say that you are familiar with Wolff, Wolff's law and all in the bone remodeling. So he actually suggested that the trabecular orientation will or may coincide with the direction of principal stresses. And I'm pretty sure that you know what are principal stresses. So in isotropic bone remodeling, so you know what is bone remodeling. So initially what we do in isotropic or orthotropic bone remodeling is that we assume the particular material as isotropic, and in the following bone remodeling process we get the particular directional, I mean the orientation or the directions, and we vary the material property accordingly. So there are several researches which has been done in this particular anisotropic bone remodeling that has been presented here by those are Dobler and Garcia 2002 and Jacobs et al 1997. And one of the main thing which you have to come which the term which you have to get familiar is this fabric tensor. So what is fabric tensor? It is the second rank tensor. So you know what is second rank tensor. So any scalar quantity is a zero order tensor. So a vector is a first rank tensor, and the second order tensor is similar to any stress tensor is a second order tensor which has got direction as well as orientation. So similar to that, fabric tensor is also a second rank tensor. But can you tell me whether elastic tensor is second order or fourth order? Does anyone know that?
Fourth order.
Elastic. Okay, fine. So here fabric tensor is a second order tensor. So Kovin 1986, you are familiar with the name Kovin. So he defines the bone anisotropy by the means of the so-called fabric tensor, which defines the principal values and the direction of bone mass distribution. So I mentioned bone mass or the mineral distribution is different when you go into the trabeculae level. So you have actually seen these different pictures 1, 2, 3, 4, 5, 6, 7, those groups. So the mass distribution varies in the microscopic level when you go into the trabeculae. So next, there are these micro FE models. So what does micro FE models mean? Like by the name it says they are micro level FE models. So rather than taking a macroscopic level model, you go into micro level. You take very thin slice. I mean, you go concentrate into a particular area, proximal area of the femur, and take large number of micro CT scans. Okay, and you study that particular CT scan data, and you put the continuum techniques into it in order to get the elastic tensor. So it's a lot of materials are behind what you call there is a lot of research which has gone into this micro FE analysis, but due to the time constraint I can't actually go deeper into it, but I will actually what you call guide you into the papers where you will find this particular techniques and analysis which has been done previously. So this is one technique to find the anisotropic property, and another what you call method is with the I mean here we are using the fabric tensor. In the micro FE models we are not actually using the fabric tensor as such. So in Dobler and Garcia, the fabric tensor is considered as an internal variable. Internal variable means which varies with the what you call time step. Okay, so but internal variable has to be tracked down. So the previous time step, the current time step, the following time steps has to be tracked down. That's why we call it as an internal variable, and we use the principles of continuum mechanics in this. So they have used the principles of continuum damage mechanics to what we call tackle this anisotropic character of bone trabeculae. And as you know, continuum damage mechanics involves damage and repair. Okay, so that's the basic principle of continuum damage mechanics. So bone resorption can be considered as cumulative damage process, and the bone as the absorption is considered as the repair process. So for going more detail into this particular research, you will have to refer to this particular paper, but due to time constraint I can't. So bone orthotropy, that's what more important to us, because most of the researchers have what you call concluded that bone orthotropy can what you call give us what you call satisfactory results, and it is less expensive as compared to micro FE models. As you know, micro FE models are very computationally expensive. That is one of the drawbacks of going into anisotropic bone remodeling with the use of micro FE models. So in this bone orthotropy, one of the best research which has been done in bone orthotropy is by Dalstra. Okay, so here he has experimentally found out the Young's modulus in 3 orthogonal directions. So as we all know, how many constants are there in elastic constants are there in bone orthotropy? Can anyone tell? Elastic constants in bone orthotropy?
9.
9. Okay, fine. So so the Young's modulus, we have got E1, E2, E3. So they are in the principal direction. So in order, first we have to get the value for this Young's modulus. For that, he did non-destructive mechanical testings. So once he got the Young's modulus, next thing is to get the principal directions. So in order to get the principal directions, he carried out stereological measurements. They are actually which estimates the 3D measurements using 2D sampling. It's more like projections. So 3D has got projection into 2D, and you take the estimates of 3D measurements using the 2D sample. So if you go into microscopic analysis, they actually get the help of mean intercept lengths. So that is more into the grain structure of these particular microscopic structures. So if you are interested into that, I will just share the NPTEL videos of this stereological measurements, or you can just Google it. You will get enough videos. So once he gets the Young's modulus values and the principal directions, he can actually get the Young's modulus in that particular principal direction. So because during the experimental study, he found the Young's modulus in 3 orthogonal directions, and he just have to align those orthogonal directions into the principal axis using the transformation. So he got the Young's modulus in the other in the principal directions, and thereby the orthotropic nature can be implemented into the analysis. And next research which I am going to discuss is using by Phillips and his team. So he actually considered the same, like a orthotropic bone remodeling, but there is no experimental study or research in this particular thing. So here what you do is you start with the isotropic assumption, and you do the analysis, and during the analysis you will get the directions in which the maximum stress
principal directions.
Yeah. The direction in which the maximum strain occurs. So that's the reason why it is called maximum stress occurs. So that is the principal directions. And you have actually taught them about the bone remodeling stimulus and all, isn't it, sir?
Yeah.
Yes. Okay. So we have actually you have actually been taught regarding this bone remodeling stimulus, the strain energy density and all. So rather than strain energy density, here the bone remodeling is based upon the strain, just the strain value. Okay. So so that's why I have written strain based orthotropic remodeling has been implemented in this work.
No, and one thing, Sabi, before they could
yes.
out.
Yes.
See, Phillips in 2016, the essence of the paper is basically on the natural bone, okay, not on implanted structure, okay. So they are trying to investigate the effect of orthotropy, okay. That the bone is basically they are trying to relate orthotropy with principal directions of strains or stresses. Okay. So they start with an isotropic model. They give the load. They calculate the stresses. The
principal stress.
Even the isotropic assumption is a reasonably good assumption, but it is more average. It gives you an average value. If you want to go deep inside to include the trabecular orientation, you have to upgrade your model towards an orthotropic. So that is exactly what they are doing. They are upgrading the model from an isotropic assumption to an orthotropic model. And in the process, remodeling, they are going through a remodeling procedure. Okay, they are basically going through a remodeling procedure within the natural bone. So how they are implementing that remodeling? That is based on the principal directions.
Strain-based.
Strain-based.
Remodeling. Remodeling is based on the strain. I mean, the stimulus is.
Remember, there is no implant in this case.
Yes.
It is not implant-driven remodeling. It is the axis of symmetry are changing. So material is undergoing some changes in E modulus values according to principal directions, and that is an upgraded material property as compared to the starting point, which is a isotropic assumption. Okay. The bone material property is getting upgraded to E1, E2, E3, and others through the remodeling process within its natural state.
Yes. So here, I mean, what so try to convey is we are not interested into the implant, we are not interested into the implant. So here we are only here they have only worked on the intact bone. So there is no implant, and the implant is not causing the bone remodeling here.
Sevi, so you just tell them about the process, how they are doing.
Okay, sir. Yes.
From isotropic model, they can get hold of the principal directions of strain. And then you go to the element level, and then what you do, you said.
Yes. So here element level, we get the principal directions and the principal stresses. And once we get the principal directions, we can actually vary the E modulus in that particular principal direction. So thereby the direction is also varied, and the Young's modulus in that particular direction is varied. So for every iterations, this particular direction as well as the Young's modulus varies, and once the iteration is done, we get the final trabecular architecture. So that's why here it is mentioned trabecular architecture is determined using the principal axis direction. So it's basically finding the principal axis direction. So in that particular direction, we vary the Young's modulus based upon the remodeling techniques. So so here I have actually mentioned the elastic constants are updated based on the strain in the principal direction. So here the remodeling stimulus is strain. So in the formulas, if you go into the paper, you will see the formulas of updation of elastic constants in the as the function of the strain in the principal direction. So you have to go into that paper to see the formulas. I'm not flooding the whole PPT with formulas.
So it is just for your additional knowledge. Students.
So similar work has been done by one of So similar work has been done by one of our seniors. So he has actually gone with the same approach of strain-based orthotropic remodeling. But here the interesting fact is that we are going into more physiological activities are being implemented into this analysis. So if you add more activities, then you will have to take the averaging. So because we are not finding the trabecular architecture, the trabecular architecture is not dependent on the physiological activity. So we are actually going into averaging for each element wise, and we get the principal directions, and the elastic constants are varied in that particular principal direction alone. So that has been done by Basil, as you all know. Basil, is familiar. So I'm just floating some pictures. So here I will discuss first picture by Matai et al. So here you can see the principal direction, the orientation. So if you can correlate with the trabecular architecture, you can actually see where the principal compressive groups are, where the tensile groups are, greater trochanter groups are. So this orthotropic remodeling is gives a clearer picture as compared to the isotropic assumption for the trabecular architecture of the bone, proximal femur. So here, similar picture you can see. It has been already mentioned. What is red and blue? The dominant directional Young's modulus are highlighted by E1 and E3. So these are just the trabecular architecture. This is just to tell you how the orthotropic or the isotropic assumption can what do you call realistically consider the model, like which is more realistic, orthotropic or isotropic. So in isotropic we are just assuming, it's more like an averaging, as sir told, but in orthotropic remodeling we have a particular
the assumption is more valid for macroscopic level model. Okay. Why that?
Yes.
I will give you a proof. There has been a very practical study that's conducted by Warhol in 2006 in the Journal of Biomechanics. Just came out. So for macroscopic level model, isotropic assumption, heterogeneous isotropic assumption is a valid assumption. Okay. But that is not too valid if you are considering, osteoporotic patient and if you are going towards a microscale model. Okay, the moment you induce more and more porosity in the bone structure, the effect of orthotropy will have more profound influence in the stresses and strains, and it will affect the results to a greater extent as compared to the isotropic. Okay.
Yes. So in a nutshell, the principal stress directions actually give you
Sebi, I think where you went a little fast, if you can go back a bit.
Okay, but it's already 1 o'clock.
Yeah, but maybe you can continue next Thursday. You give time for the students. What I would advise that this is little bit high level stuff. Okay, to be honest, but I'm trying to just highlight the difference in the properties, because nowadays many materials, okay, the new generation materials are actually mimicking bone structures. Okay, this is an important message for the students. There are a lot of porous, lattice structured, materials that are evolving for specific application, load-bearing applications as well. Okay, so the internal structure of the material, the porous structure, the lattice structure. Lattice is more a regular porous structure that we call lattice structure. So that are evolving nowadays, and people are learning from the nature to design more sort of porous structures that can serve the basic purpose of as compared to solid structures. So there are many sort of applications where porous structured material are preferred than solid structured material. Okay, and everything evolves from here. That the moment you induce porosity, it will have directional properties, and these directional properties may not give you the same result as you would assume it as a solid continuum material. Okay. Please go through it. Next Thursday, what I would advise, Sebi, that you repeat this class, you continue discussion with the students next Thursday, not Wednesday. So you can continue discussions, show them again the slides, because they also have to understand. This is little bit high level stuff, let me tell you. It's not very straightforward.
You have to read papers to understand it. You can't actually
ask them to read these things. Oh, they have so many things to read, so let us not expect too much. But
no. I won't ask them to read, because it's like you need to put a lot of effort to understand this particular thing. I mean, you will obviously have some doubts, like how these are what you call updated. in the principal axis directions. But those are actually more like implementation. So this theory and implementation has got a gap. So
Yes.
that gap has to be filled through literature review actually. So once you read the papers, you will understand more. So I
Yeah,
can
just to
focus on
on next Thursday, what you can do is give them a
Yes,
little
yes,
bit
yes,
more
yeah.
idea, because
Yes.
they get more educated by this time.
Yes, yes.
Uh,
And I will have to tell one thing to students that before you submit this